This is Hampton Court, which stands beside the River Thames in Surrey. The oldest parts of the palace date back to 1514. It was built by Cardinal Wolsey, and he gave it to Henry VIII, who enlarged it. And then in the 1690s, Sir Christopher Wren added a new wing for William III. The last king to live here was George II in the early 18th century. Well, I'm now in the middle of the famous maze, and this presents me with a very interesting problem. Just how am I going to find my way out of here again? Well, it just so happens, over here, we have a copy of Unit 5. And if I open this at page 29, yes, there, in fact, is a plan of the Hampton Court maze. Well, the snag is I'd better not follow this because I rather suspect it's out of date. What I will do is to turn over the page because over here we have a description of an algorithm due to Tarry, which is an infallible way of finding your way out of any maze. And this guarantees that you won't trace any path in the maze more than twice, and that's very important. It's all right finding a theoretical solution. We need a practical solution that will get me out of here in a reasonable amount of time. So at least there's one problem I've got solved. Now, problem solving has been our concern throughout this course. Faced with any practical problem, we've always tried to construct a mathematical model and then use combinatorial techniques to find a solution. Just what kind of solutions did we come up with? Well, sometimes we were able to give an actual explicit solution. And this was so in the case of the problème des ménages.
In a dinner party involving 3 couples, one thing we can notice is that if we wish to seat, say, the ladies so that they're not sitting next to their husbands, and men and women are sitting alternately, there's only one way of doing this. But if we increase the size of the party, the problem becomes less simple. Good day, gentlemen. Here we're preparing a dinner party for 5 couples. How many ways are there that we can seat our wives in alternate seats round the table so that no wife is sitting next to her husband? Well, let me show you how I'd work it out. I'd need to have 5 columns, 1 for each lady, and 5 rows, 1 for each seat. Now, I wouldn't want to seat my wife in seat number 1 next to me, so I'll put a mat on the table there to show that that square's prohibited. I wouldn't want her in seat 5 next to me either. And for my first guest, I don't want to sit his wife in seat number 1 on this side of him, or in seat number 2 on the other side of him. And so on round the table. For every lady, there are 2 seats that we don't want to sit her in. And to find out the total number of ways of seating the ladies as we want them, we'd need to find the appropriate coefficient of the root polynomial for the white squares. But there are fewer green squares than white ones, so we'd use Roy's theorem to work this out. This problem, in fact, turns out to be very similar to the jobs problem. Have a go yourself at solving it after the programme. We've given you the solution in the broadcast notes.
Well, root polynomials gave us a complete analytic solution to that problem, and to many others besides. That, of course, is one of the main aims of this course, to provide you with the techniques that you'll need to tackle whatever combinatorial problems you might encounter. Now, as we saw, root polynomials are a very versatile tool in quite a wide variety of enumeration problems. Counting is at the very heart of combinatorics. Historically, it was one of the first areas of the course to be developed. We've perhaps spent rather less time on counting than we might have done. We've been rather more concerned with construction problems. And a fascinating example of this occurred in connection with the Mariner 9 space probe. Well, how do you like my new wallpaper? It's a very interesting pattern, and like most wallpaper patterns, there's more to it than meets the eye at first glance. This particular pattern is of special interest to us. If you remember, a little while ago, we were looking at the instance matrix of the Fano plane. Something very interesting happens if you try to superimpose that instance matrix on this pattern. Let's put it somewhere down here in the bottom right-hand corner and just watch what happens. Well, can you see that all the zeros are on blue squares and all the ones on yellow. So the colour reflects the digital pattern. Now you remember we used the instance matrix of the final plane as a code. So we've already seen the pattern of one code embedded in this wallpaper. In fact, there are many more. This in fact is a very important pattern, so I think I should show you just how it can be constructed. What I'm going to do, in fact, is to start off in the top left-hand corner. I'll start off with a single blue square. And then I'm going to do, stage by stage, exactly the same thing. I'm going to reproduce what I've got so far to the right. So in this case, it's just another single blue square, another blue one below. And the gap I'll fill in with the same pattern, but with the colours reversed. Well, I've only got one colour, blue, so I get yellow. That's the end of the first stage. I repeat the process. I take the pattern I've got so far, here it is, and I reproduce it to the right and below. And then I fill in the gap with the same pattern with the colours reversed. So here I have 3 yellows instead of 3 blues. That's the end of the next stage. Again, the same thing all over again. I take the pattern I've got so far and I put it down to the right, and the same pattern below, and I fill the gap in with the same pattern with the colours reversed. Well, I could go on like this indefinitely. If I went on just one stage more, I'd get the wallpaper pattern, which is behind me, and if I went on a further 2 stages, 3 stages and all beyond this, I would get a pattern that included within it the pattern of the code used by Mariner 9, but that's just too far for us to jump. Coding theory may seem to be one area where the existing techniques cope very well with the kind of practical problems encountered, but you can be quite sure that the coding theorists find lots of difficult problems to occupy their attention. It always seems to be the case that no sooner do you solve one problem and there's a whole lot more waiting for you. But sometimes just one problem can present a major challenge. And the classic example of this was the famous 4-colour problem. Listen again to Professors Appel and Harkin describing the difficulties which they encountered before they finally settled this long-standing question.
Well, the first difficulty was that it wasn't clear that the conjecture was true. And if it was true, it wasn't clear that it could be solved by Kemp's technique. And if it could be solved by Kemp's technique, it wasn't certain that this could be done in a reasonable length of time. For instance, if the number of configurations was too large, or if the time it was required by computer to check one configuration was too large, the problem would be impossible. The difficulty in checking reducibility depended on the size of the configuration, where the size is measured by the number of countries neighboring the configuration which were not in the configuration. If the size was 8, it would take quite a while by hand. If the size was 14, it would take 4,000 times that long by hand. The second problem was the general problem of finding unavoidable sets of configurations which hadn't been studied sufficiently thoroughly at that time.
So what approach did you take, Professor Harkin?
Well, we had a method of estimating how likely a configuration was to be reducible. Of course, that was not a sure thing, but it had about 80 to 90% accuracy. And so we started to first find an unavoidable set of likely reducible configurations in order to see how large the set would be. And much later, we started really having a computer to check reducibility. So that was a fortunate strategy, which saved much computer time.
We know that you had to use a computer to establish the reducibility of about 2,000 configurations. So that we can get a feeling for this, how long would it take to check the reducibility of just one configuration by hand?
For one of the more difficult configurations, we would estimate that a man who was working a 40-hour week would take about 5 years to check the type of output a computer might give.
It would be a pile of paper like this just for one configuration, if we had the computer print everything. Now you imagine this 2,000 times. 2,000 times that high would be higher than the Empire State Building.
When did you first come to realize you could actually prove the theorem?
In the spring of 1976, we became more and more convinced that eventually we would be successful. In June of 1976, we were sufficiently convinced to write a note on our departmental blackboard which read, "Modulo careful checking, it appears that 4 colors suffice."
Well, that was essentially an existence problem. Does there exist a map that requires 5 colors? And the answer, as Apple and Harkin finally proved, is no. Very many problems can be expressed in the form of a question to which the answer must either be yes or no. And these form an important class of problems that we call decision problems. And they include some very difficult problems indeed. And this we shall see shortly. Now, you'll have noticed that Apple and Harkin had to use a computer to help them with their problem. The point is, of course, that computers calculate so fast as to be able to complete calculations that would require us a whole lifetime or more. Well, of course, their computer program is just an algorithm expressed in a language the machine can understand. And algorithms are often featured in our course. Here's what Program 11 had to say about transportation algorithms. Well, here's a fairly basic example which I'm going to work with. I'm supposing I've got 3 factories, and I'm looking at their maximum outputs, which are respectively 4, 7, and 6. Then over here we have 2 customers, and they have certain requirements. We have 8 and 9. Now you'll notice at once that the maximum output, 4 plus 7 plus 6, well, that's 17, which is exactly the same as 8 plus 9, the requirement. Now the transportation costs from each factory to each customer will depend upon the distance and upon various other factors. What we're going to do is to look at the cost per unit, that's to say the cost per module. And so we have 5, 4, 3, 3, 2, and 5, respectively. So here then is the essential bits of our model. We've got certain outputs, certain requirements, and we know the cost of transporting one to fulfill the other. Now, of course, any real-life problem would be much larger than this. And also we've made certain simplifying assumptions, but never mind, we've got here all the essential features of the problem. Well, here again, we have the flowchart for our algorithm. Now, this is, of course, not the same as the Hungarian algorithm that you find in the text, because that has a different flowchart, and here it is. Well, you're quite right. Both diagrams do have the same block structure, but, and it's a big but, the course of the algorithm is entirely different. For example, look down here at the test condition. To ask if the required flow has been reached is just the same thing as saying, is the solution feasible? Now, finding a feasible solution was the very first step in our earlier algorithm, do you remember? But the Hungarian algorithm finds a feasible solution only at the very end. It finds the optimum in an entirely different manner. You might say it approaches the problem in reverse. However, if you care to apply the Hungarian algorithm to our simple problem, you'll find it reaches precisely the same solution as we did. It may not be obvious that the Hungarian algorithm does always produce an optimal solution. But at least we know that it does with our example, because it reaches the same solution as the previous algorithm. Well, is there any reason for choosing one algorithm rather than the other? Each has its merits. The first algorithm is probably easier to work by hand, but the Hungarian algorithm tends to be more efficient. And so it's well suited for the solution of large-scale transportation problems, particularly with the aid of a computer. So we've got 2 algorithms for that particular optimization problem. Now, what does it really mean to say that the Hungarian algorithm is the more efficient of the 2? Well, just this. It takes less time to solve a particular problem than the other algorithm does. Now, of course, it's quite common to find that one computer program is faster than another. After all, some programmers are better than others. But what we're talking about is a more fundamental superiority of one algorithm over another. Just look at it this way. Computers certainly operate very fast, but nevertheless, some problems require such an enormous amount of calculation that they take a lot of time even on a computer. And then the difference between an efficient and an inefficient algorithm can be of great significance. Let's listen to what Eric Scheffner had to say about the computer model of the supergrid.
We couldn't possibly model the whole of the distribution system. There are too many cables and too much detail. So what we do is we select the major distribution lines that transmit large amounts of power around the country, and we make a model. In practice, this means the supergrid, that is the 275 kV and 400 kV systems. In the model, the substations are treated as sinks. The model, in fact, is the top layer of the grid system. When we study regional level, we take the results from the first layer of the model and add the detail of the regional systems, that is the 132 kV network, again representing the network as sinks, sources and arcs, and so on, adding the detail down the various levels until we get down to the consumer networks, studying smaller and smaller areas. Here at National Control, we're only concerned with the supergrid, that is, the top layer of the grid system. In the model, the main sources are our power stations. The substations are treated as sinks, and the transmission lines as arcs of the network. Although we have simplified the network, it is still a complex network diagram, but it gives us useful results from a workable model. This is a printout from the computer model. The model is fed with predicted data for the following day's demand and shows the likely bottlenecks, that is, lines that could be overloaded if a single line fails.
You said that the model was fed with predicted data. What happens if the predictions turn out to be wrong? For example, if it's a fine day unexpectedly?
We use a second model which takes actual data direct from the power system. This data is transmitted to our regional control centres and is then sent on to our computers at National Control.
But can you imagine what would happen if the computer model used an inefficient algorithm? Absolute chaos. You'd find that the computer would predict several hours later what it thought would happen about an hour after it started. In other words, it would tell you about 5 o'clock what it thought was due to happen 3 o'clock. Now, it might seem that all you've got to do is to be sure to hire good programmers, and in some cases that's certainly true. However, there are some problems which no programmer, however good, can produce a result in a reasonable time. And unfortunately, combinatorial problems are very prominent amongst these difficult cases. Nevertheless, not all combinatorial problems are difficult in this sense, so let's begin by looking at one of these.
When we make a mathematical model, what we're doing is to pick out the important aspects of a system and to represent them in a mathematical way. And over here, I've used a digraph to model a system of one-way streets. The arrows on the graph show us the direction of traffic flow, and I've used these numbers in circles to give us the length of each street, so that I haven't had to make the digraph a scale map. Now, in this example, there are lots of ways of getting from S to T, and my problem is to find, again, the shortest one. We could look at all the possible routes, but in a large network, that would give us just too many to look at, and we couldn't be sure we hadn't overlooked one. So what we need is a systematic step-by-step procedure, in other words, an algorithm. And these rings are going to help me to describe one. The algorithm itself you'll be meeting in Unit 5, so we won't worry too much about the details for now. I'll just go through the bare essentials with this example. And I'm going to use these rings to give me the distances of each vertex of the network from the starting point S. Now, the algorithm depends on the fact that if I'm on the shortest path, somewhere in the middle of the network, I must have got to any intermediate point by the shortest path from S to that intermediate point. So we start by exploring the 4 paths from S. And we can see that A is a distance 7 by the direct route, so I'll put a square for A at 7. B, similarly, is a distance 4, C a distance 9, and D also a distance 7. Now, if we look at the innermost one of the black squares I've put up, this is the one at B, we can deduce that the shortest path from S to B is by this direct route, simply because any other path would have to be a 2-stage one, of which the first stage is one of these 3 longer routes. So I'll note that we've already found the shortest path from S to B by changing B's square from black to white. Now we go back and repeat the process. We explore the paths from the white square at B. And that's the end of my algorithm. I've looked at all the routes to get to T, other than those that we know aren't the shortest. And the shortest one I've found is this distance of 10. So I can change that black square for a white one. And we remember that this shortest route to T came via C. The route to C with a distance 7 came via B. and the route to B with the distance 4 was direct from S.
Now, the shortest path algorithm is an example of what's known as a polynomial time algorithm. What this means is this. Suppose you have n vertices, that's the size of the problem, and the time taken to solve it increases only as some polynomial in n. And this means that it doesn't, for example, increase exponentially, which would be much faster. Unfortunately, many problems can be solved in polynomial time. This class of problems is a class which is called P. On the other hand, there are some problems which no polynomial time algorithm is known. An example of this is the travelling salesman problem. All known algorithms for this take an inordinate amount of time as soon as you have more than a few cities. On the other hand, you can express the travelling salesman problem as a decision problem. Look at it this way. You can say, does there exist a route of total length less than, say, some quantity L? The answer to this, of course, is just yes or no. Just imagine that by some miraculous method you were able to guess the answer, or at least to guess a route. Then you could check whether this route was or was not less than length L in polynomial time. And this gives a new class of problems that we call NP. Now, late in 1979, there were rumors circulating that a young Soviet mathematician had found a polynomial time algorithm for the travelling salesman problem. And mathematicians were quite amazed at this news, because if it was true, it suddenly meant that a whole class of problems could be solved in polynomial time. And the reason for this is that the travelling salesman is what's called an NP-complete problem. What it means that in the form of a decision problem, you can express any other NP problem in terms of the travelling salesman. Now, unfortunately, the reports were in fact misleading. What the Soviet mathematician had actually come up with was a new algorithm for linear programming. And certainly it's possible to translate quite a lot of problems and express them as a linear programming problem. The snag is this, however, that the translation itself takes exponential time. So I'm afraid these problems are just as difficult as they ever were, and there are lots of problems like this in combinatorics. Perhaps that's what gives the subject its fascination. There are lots of problems for you to solve. Good luck.